Well, hello, I'm back, and I think I've got a very cool hack for you here. The goal here is to hack complex fractions, and you're seeing three cases here from arithmetic. Think of this as complex in the numerator, and this case over here we're complex in the denominator, and this is a combination of the two cases. We're complex in both the numerator and the denominator. The hack I'm going to show you will handle all three cases. To keep this sort of wedded to the real world, think of this problem as a recipe problem. We've got some cookies we're making that call for 3/4 cups of walnuts, and we're going to make only half the recipe. So how many cups of walnuts do I need? This calculation will get us home. Over here, this is actually from baseball. Computes the earned run average of a pitcher. It turns out to be the primary statistic for evaluating performance of pitchers. In this case, the pitcher has pitched 12 innings, which we divide by 9 in the bottom because there's 9 innings in a game. And in those 12 innings, he allowed 6 runs. If you crunch this out, you get his earned run average, which turns out, like I said, to be the primary statistic. And the middle case, where we're complex in top and bottom, that's actually a problem that appears in calculus a lot and is the origin of my hack. The reason why I created this shortcut, because I got so tired of doing this the conventional way, the blundering, bumbling way that it was taught to me in L-High. I had to come up with something new. Now, of course, we're not talking about these particular numbers, but in calculus, quite often, you'll have an arithmetic problem where you'll have complex in both top and the bottom. And I'm going to come full circle at the end of the video and actually show the derivation of this. Okay, so what about algebra? Well, it turns out that my hack will handle this situation right here with ease. It will slice and dice this no problem. What you're going to learn in the three above problems is totally applicable when you have unknowns and algebraic numbers like we're seeing here. The case where the hack doesn't work, though, and that's really critical. Here is that case. This also appears in college and intermediate algebra textbook problems. And the reason why it won't work is because the hack is reliant upon the only cases where you have fraction over fraction. And in this case, we have a single fraction in the top and a single fraction in the bottom. But in this case, we have a fraction in the top, but we have an addition of two fractions in the bottom. And so it will not work here. But what's beautiful about the hack, and I'm going to return to this too, is that the thinking that is used to simplify this is actually the same as the thinking behind my hack. And so there's a continuity. The hack lends itself to the solution of these more complex problems. Okay, so let's show the way it's taught, the blundering, bumbling way that I was taught in L-High to handle these complex fractions. Here is the case where we're trying to find out the number of cups of walnuts we need. The way it was taught to me, and still taught, is you write this vertical division horizontally. First step. Second step is you write everything over 1, any whole numbers over 1 to create fraction divided by fraction. So that's why I put the 2 over the 1. And then the third step is the magic step that no one can explain, and I think is the moment when math goes south for a lot of people. And it's no wonder. I mean, here, what's going on here? We're changing the division to multiplication, and we're flipping the fraction. In other words, the phrase that's pounded away into people's heads is invert and multiply, invert and multiply, invert and multiply. But nobody knows why that works. In fact, I would actually issue in a challenge. If you are a teacher and you're teaching calculus or even algebra, offer bonus questions to explain to you what happened there. You know, why? What's going on there? How can you invert and multiply? What's the reasoning behind that? And even a class of calculus students will stutter and stall out on that because it involves some abstract algebraic reasoning that gets glossed over and is taught before its time. Now, so far we've had 3 steps. There's actually a 4th step. You have to be swift enough to remember that you multiply fractions straight across. And so we do that to get 3/8. So there you see it. 4 brutal steps. And all I can say is, you know, are you kidding me? Are you serious? Is this really what we want to teach? Is this the technique that we want to teach our kids? And I say it's not. If we're going to teach them calculations, we want to teach them the best calculations, the simplest calculations, and the ones that point forward to algebra and calculus. And that is the idea behind my hack. So here is that first problem done with the hack. Now I call it drop the denominators. That's the name of the hack. But since we're only dealing with a complex in the numerator here, we're singular. Drop the denominator. And what the hack says is you just drop the denominator into the bottom. So the 4 is going to drop down here as a multiplier. And I'm going to get 3 over 4 times 2, or 3/8, and I'm done. One step. And I want to show you the argument, the technical teaching argument for why I think this is the way we should be teaching how to handle complex fractions in our elementary schools and colleges and high schools. The magic behind drop the denominator is accessible and leads forward. Here is that same problem, and I am showing you the magic behind the scenes. What I'm really doing in the hack is I'm multiplying by a fancy form of 1. You can multiply by 1 and not change something, of course. And so I'm multiplying by 4 over 4, which is 1. And what happens here is the 4's in the top cancel, and I'm left with just 3 on the top. And on the bottom I've got 2 8s. 2 times 4 are 8. And so that's the magic behind the hack. I simply eliminated this step right here, the multiplication by the fancy form of 1. And instead created some lingo to describe what's happening, namely the denominator is being dropped. Now, why does this lead forward? Well, consider that problem I said that the hack does not handle. This is the more complicated sort of complex fractions that you see in college algebra. Again, to simplify this, you're going to, just like the hack, you're going to multiply by a fancy form of 1. But in this case, what you're going to multiply by is the common denominators to all 3 fractions there. And it turns out that would be x over y times x over y. And the same thing would happen here. The x's would cancel in the top, and the y and the x would cancel in the bottom, and the fractions would disappear. So you could see, I'm not going to work this problem out, but you could see the same technique is in evidence here. And it so my hack lends itself to what happens next. Now, let's further cement the hack in our minds. I want to do the earned run average problem, the baseball problem, where we're once again a singular case. We're going to drop the denominator, and we're only complex in the bottom. And so the game here is to drop the denominator, in this case 9, but we can't drop it. There's no fraction below. And so what we do is we drop it into the top. We're still dropping it just into the top. And so we have 9 times 6 over 12. Now, many of you would rush ahead and say 54/12, but so much of any chapter on rational expressions and functions, it's all about staying your hand. Don't doing the multiplication. Wait a bit. See if something cancels. And so I purposely didn't do the multiplication here, and instead I factored the 12 into 2 times 6 to show you that the 6 cancels, and we're left with 9/2. So there you go. That's the 2 cases that mimic some aspect of the real world, where we were complex in the top and then alternatively complex in the bottom. The third case was the one that I said sort of gave me the idea for this, and this is where you're complex in both top and the bottom, which happens a lot in calculus. And to really hammer this home, I wanted to write these things in parentheses like that, so they're more apparently factors, because that's what we're dropping. When we drop the denominators, we're dropping factors. And I'm going to do that in real time. I'm going to drop the 3 into the bottom as a factor, like this. And then I'm going to drop that 5 into the top as a factor, like this. Now we're no longer complex in the top, so I can get rid of the fraction bar. And we're no longer complex in the bottom, so let's lose that fraction bar. And all we have to do is clean up, tidy it up, and look to see if anything cancels. And I think you can see nothing's going to cancel here. And so we simply finish the multiplication out, and we get 5/18, and we're done. So this is really just a case, the first 2 cases combined. We drop the 3 into the bottom and drop the 5 into the top, and we're done. And you can see the way this really eliminates the possibility of errors. It simplifies things down, and of course, like I argued before, it leads to what comes next in more complex math classes. Okay, that is the drop the denominator hack. And just to finish this up, to come full circle from elementary to high school and to calculus, from arithmetic to integration, I thought it would be nice to actually step up and to the plate and to show you some calculus and to show you why I came up with this hack. Now, so I want to do drop the denominators in calculus, and I wanted to show you, if you've seen some of my videos, you know I use PERMDAS a lot. I think it's an outstanding scaffolding, not only for teaching the order of operations, but for teaching the actual philosophy of algebra, the Tai Chi of algebra, the doing and undoing. You know that these guys are inverses of each other. Addition and subtraction, multiplication and division, roots and exponents. And with calculus you get two new operations, differentiation and integration, and they are in fact inverses of each other. And you know what's really curious about this, you might not have noticed this, but in this scaffolding here, subtraction is harder than arithmetic. Division is harder than multiplication. And taking a root is harder than exponents. And similarly, in calculus, integration is notoriously more difficult than differentiation. And I'm going to actually do some integration because that's the case where these drop the denominator problems appear all the time, and show you that as sort of a motivation to actually do it this way. So let's do some integration. And here is a polynomial. It's a polynomial because the exponents are positive integers and the coefficients are real numbers. There's a 1 out front here and there's a 2 out front here. What I want to do is bring in the integral sign, and I want to take the integral of this polynomial. And it's actually simply done. This is one of the easier ones, first semester calculus. And let me show you what that operation involves here in this case. What you do is you simply add 1 to this, and you would get x to the 4th. And then whatever you get when you add 1, in this case 4, you divide the coefficient by that. So you're going to get 2 over 4. So when I integrate this first term, I get 2/4 over x to the 4th. Now let's do the second term just to nail it. Again, I'm going to add 1 to the exponent, so I'm going to get x to the 3rd, and then whatever number is out in front, I'm going to divide it by 3. So I'm going to get 1/3 x to the 3rd. And there you go. I pretty much have integrated that polynomial expression. Now, why would you want to do that? Well, obviously it's beyond the scope of this video, but essentially this will give us really valuable information, especially in applications, about what's going on here. It turns out that we could learn a great deal about what's happening here by evaluating this for certain values of x. So that's integration, but no complex fractions came up, but they do, and I want to show that now. Here is another case, another non-polynomial, but polynomial-like expression that we're going to integrate. It's not a polynomial because this is not a positive integer. It's a fraction. I want to bring in the integral symbol. I want to integrate this. It's the same game. We're going to add 1 to this, and so we're going to add 5 over 5, 1/5 plus 5/5, and we're going to get 6/5. And whatever out in front is going to be divided by 6/5. So we're going to get a complex fraction. We're going to get 1/3 over 6/5 times x to the 6/5. And that is integration. But of course, your teacher is going to want you to simplify that complex fraction. And thus, this happens all the time, 10, 20 times in a problem set. And I got so tired of stumbling at this moment that I created the hack. And it was only later in life that I realized that the hack lends itself to elementary school, high school, and college, that it is continuous and fits in really nice for the evolution of complexity as you go through those courses. So there you go. Let's run the hack on this one more time. We drop the 3, we drop the 5 into the top. On top we have 5 times 1. On the bottom we have 6 times 3, or 18. We have 5/18 times x to the 6/5. There you go. We've taken the integral and we've handled the complex fractions. Okay, I hope that helps. Be talking to you again soon.